Hello students, in this video we'll discuss the order of magnitude of decay of Fourier coefficients. Let's suppose, to start, that f maps negative pi to pi into c, 2 pi periodic. Okay, and let's initially assume, so here's the first case, so this is going to be case 1, so case 1, let's assume that f is in the class C1 of t, which is all functions are continuously differentiable. So this is the set of functions f mapping the unit circle. This, of course, is our shorthand for the unit, the torus, into c, such that f and f prime are continuous in 2 pi periodic. Okay, so in other words, the derivative is going to be a continuous function. Those are the C1 functions. Let's figure out how fast the Fourier coefficients will decay in this case. Well, let's look at f hat of xc, f hat of n. That's the nth Fourier coefficient. It's going to be 1 over 2 pi, integral from negative pi to pi, of f of x e to the minus inx dx. And here's the mechanism by which Fourier coefficients decay, at least one of the mechanisms. The first mechanism is I can integrate this by parts. I'm going to let this be my u. Remember now I can differentiate f because the f prime is continuous over here. And this is going to be my dv. Okay, so if we integrate by parts, what we're going to have u times v, so 1 over 2 pi, and then f of x times an antiderivative is going to be e to the minus inx over what? Over minus in from negative pi to pi, minus the integral from negative pi to pi of v du. So that's going to be an f prime of x, and then what? And then e to the minus inx over minus in dx. So I integrate by parts, and this is what we get. Now, the important thing to realize here is that these functions are 2 pi periodic, right? So these are 2 pi periodic functions. So when I plug in pi, this function over here is 2 pi periodic, and this function over here is 2 pi periodic, right? So if I plug in points that differ by 2 pi, then I get the same value at the top and bottom limit. So by 2 pi periodicity, those boundary terms are gone. So that follows from 2 pi periodicity. 2 pi periodicity implies that those terms are gone. And so what we see over here is I see that now I have this expression here, the f hat of n, so hence f hat of n, in this case, is going to be, negatives are going to cancel out. It's going to be a 1 over 2 pi. I'll pull that I and n out, I and then n, and then integral from negative pi to pi of f prime of x, and then e to the minus inx dx. Let's make sure I have all the terms. So I have a 2 pi, I have a 1 over n positive term, and then we get this formula over here. So by integrating by parts, we get this. Now, how large can f hat of n be? So by taking absolute values, f hat of n is less than or equal to 1 over 2 pi n, integral from negative pi to pi of f prime of x, put the absolute value inside the integral, and then of course the absolute value of e to the negative inx, the modulus of that is just equal to 1, it's unimodular. And now the function f prime is continuous, so it's bounded on this interval, so there's some number over here, m, such that this is going to be m over n, just for some constant n. So that says that the Fourier coefficients decay like 1 over n. So in other words, that we get this rate of decay for growth over here, right? And so now I can apply this reasoning k times, right? So hence this generalizes. So in general, if f double prime is continuous, I can do this procedure twice, right? And so hence, if f is of ck, suppose that f is of class ck on the torus, then this implies that the Fourier coefficients, by the same argument over and over and over again, that f hat of n decays like what? A constant. That constant depends on k and pi and the bounds on the derivatives and everything like that, over n to the power k. So in particular, what this tells us that the function is of class C2, so hence this automatically implies by our absolute convergence result that if f is of class C2 on the torus, then this implies that f of x is actually equal to its Fourier series. Its Fourier series converges absolutely and uniformly to the function itself, f hat of n e to the inx. In other words, when f is of C2, we have a Fourier convergence result. Now, the last result we'll talk about in this case, I'm going to talk about the second case when we don't have we don't have exactly one derivative regularity, we have Holder regularity. So now let's suppose, this is case 2. So in other words, case 1 deals with the case when you have derivatives, right? You have a first derivative, or second derivative, or a kth derivative, right? And the kth derivative in this case is going to be continuous. So over here, the kth derivative is continuous. Okay? That's what this means over here. So if you have continuity derivatives, you can get further and further decay of the Fourier coefficients. Case 2 is, what if I just have the Holder continuity? Let's let alpha be between 0 and 1. This is the Holder class. Then Holder continuous implies what? That says that f of x minus f of y is less than or equal to a constant, x minus y to the power of alpha. That's the Holder continuity, okay? Of order alpha. Okay. Now, if your Holder continuous of order alpha, you still get some decay estimates over here. And so here's the idea. So here's the proof of this fact. So now let's look at, I can say that f hat of n is also equal to this. I claim that if we make a substitution in the Fourier coefficient definition over here, so in other words, if I let x be y plus pi over n, that'll give me a negative sign, right? So this is going to be negative 1 over 2 pi, the integral from negative pi to pi of f of x plus pi over n e to the minus I n x dx. We can see this, of course, just by changing the variables, right? If I treat this variable over here as y, I'm still going to, by periodicity, I'm going to get an interval of length 2 pi again, so I'm going to integrate from negative pi to pi by periodicity. And then what will happen over here, if y is x plus pi over n, this is going to turn into an e to the negative I n pi over n with a minus sign. That's going to be a minus sign error, so that generates a negative sign. But what this allows me to do is this allows me to symmetrize, right? So by symmetry now, so I know that f hat of n is equal to this expression where I shift it over by pi over n, and it's also equal to this expression over here. So if I average those expressions, I get another expression for the Fourier coefficients. So by averaging, hence, okay. Hence what? Hence, f hat of n is going to be a 1 over 4 pi if I were the negative. We're going to leave it as positive. I can do this thing. I want to do this thing over here. The negative of this, so if I make that negative, then we'll get this, right? Integral from negative pi to pi. It won't actually matter. I was just going to say plus or minus, so it won't matter. F of x plus pi over n minus f of x e to the minus I n x dx, like that. And now if I put absolute value everywhere, what's going to happen over here? If I put absolute values on this, less than or equal to this, and now the difference between f of x at pi plus n and f of x is pi over n, right? And this thing over here would be unimodular, so this will be less than or equal to some constant, this number over here, pi over n to the power alpha. So this is going to be some huge constant over n to the power alpha. So the Holder continuous functions, their Fourier coefficients, if your Holder continuous over order alpha, your Fourier coefficients will decay like 1 over n to the power alpha, and that's actually a sharp estimate. You can construct Holder continuous functions of order alpha whose Fourier coefficients, at least on the dyadic numbers, are basically exactly equal to 1 over the mode to the power alpha. So in other words, this is a sharp estimate for the Holder continuous function. So, but nonetheless, we get some decay estimate for these Holder continuous functions over here, and we're going to see how these estimates on Holder continuous functions help us solve partial differential equations, help us get regularity for certain classes of PDEs. It's a very, very powerful result. So we'll see that in further videos. Thank you very much.